Hi there. So in this video, I just kind of want to give you an overview of vector calculus. Most people call this course vector calculus. I prefer another word called multivariable calculus that we'll see later, and vectors are tied into that. But to start getting an idea about what vector calculus is about, there's just a basic notion of what it's about. And it's this idea right here that we're just doing calculus in higher dimensions. All right, and so now that's an easy thing to say, but one way you can think about it is we're just taking everything that we already know about calculus and extending it to the idea of having more than one independent variable. And if you don't remember some of these terms, we'll go over that. Okay, but because of that, you can see that this idea, if we're talking about doing calculus in higher dimensions, we need to have a good idea about what this word dimension means, at least a workable one for now. So to start talking about this idea, first of all, we've got to talk about spatial dimensions. Okay, so these are about spaces, and you'll understand what I mean, the difference in a minute. But there's other things that have dimension. Okay, and so for a moment, let's just skip this 0 and 1. You might not have a pretty good sense of that, but a two-dimensional space is basically a plane. All right, and if you remember what a plane is from geometry, it's basically an infinite piece of paper. Okay, and in some cases it doesn't even necessarily have to be infinite, but for most cases, whenever we think about a two-dimensional space, we think about it being infinite. So we think about that as being an infinite piece of paper. Sorry about that. Okay, like that, and then. Three-dimensional space, basically it's the space we live in. Okay, and so one way you can think about it is being an infinite box if you need to. All right, and we'll use that idea, and we'll do a lot of work in 2 dimensions and 3 dimensions. You can kind of follow the pattern backwards now to understand what one-dimensional space is. One-dimensional space is a line. Okay, like that, and then 0 dimensional space is just a point. Okay, those aren't necessarily the most important things for us right now, but it is important to understand that a line is one dimensional. Okay, and make sure you realize we're just constrained by our senses to 3 dimensions, but there are higher dimensions, and especially for very practical problems in agriculture and meteorology and all kinds of finance and so on. You end up needing to work in a higher dimensional space. So try not to limit yourself to thinking everything is just 2 dimensional or 3 dimensional. Just because we can't perceive things in higher dimensions doesn't mean that they are there. Okay, now we want to talk about the dimension of things, and this is where it starts leading into multivariable calculus. Okay, and so we just agreed on the last slide that a line is one dimensional. Okay, and so what does that mean? That means that this thing right here is one dimensional. Okay, it's a line. But notice that I drew the line in a plane. My screen is a part of a plane. All right, so I have a one-dimensional thing drawn in a two-dimensional space. Okay, and now there's a way you can use variables to understand dimensions of objects. So if we think about now taking that line and drawing it in the Cartesian plane, all right, then we know that that line has some equation. Y is equal to mx plus b. And remember, m and b are constants, right? Like that. And so the key thing here is that we have two variables, okay, but y depends on x, okay, like that. And so what we have is one independent. So remember, x is called the independent variable, right? Like that. And so what we have here is one independent variable. Okay, and that ends up being a way we can identify the dimension of objects. Okay, and so one way to think about what the dimension of objects, a thing or an object, okay, and I'll just say the dimension of a graph right there, okay, that's going to be the number of independent variables. All right, and so that's one way we can isolate that. All right, that leads into another nice thing is if we think about a circle, okay, and again, thinking about drawing it in the XY plane, Okay, now you might have to remember some basic algebra, but the equation of that thing is x minus the x naught squared plus y minus y naught squared is equal to the radius squared. Okay, that's the general equation of a circle in the plane. All right, and so now think about trying to solve this thing for y. You could move the x minus x naught squared over to the right side by subtracting it. Okay, and then taking the square root of both sides, and you could add the y naught over. So you would end up getting y is equal to y naught. Remember, whenever we take the square root of both sides, we have to do that plus or minus, and then we would have the square root of r squared minus x naught squared. Don't worry too much about the algebra that I'm doing right now. I'm just saving some time in my video. But the key thing here is y naught, r, and x naught are all variable, are all constants. Okay, so these are constants that you fill in to get this equation right here. Okay, so notice that y depends on just one variable. Okay, and so in this thing, x is the independent variable, and it's the only independent variable. Okay, and so what we're seeing here is a circle is also one-dimensional. Okay, like that. So now one important thing to realize, we're just talking about the circle. So whenever we talk just about a circle, we're just talking about this part right here. Okay, we're not talking about the inside. If we included the inside here, that would actually be two-dimensional. All right, but we're not talking about doing that. We're just talking about the circle all by itself. The equation of just this circle is this. It only has one independent variable. One other thing too to point out is we could have just as easily solved this equation for x, in which case we would have x equals x naught plus or minus, and then we would have had y minus y naught squared. So in that case, y would have been the independent variable. So in a lot of cases, for graphs that aren't functions, there's not a clear independent variable, but you can solve to get just one independent variable. Okay? So now if you think about it, if lines and circles are one dimension, we can think about a lot of things that are one dimensional. Function graphs, okay, like that. And so anytime we have y equals f of x, like that, then what that's saying is that there's one independent variable, okay, like that. And so, again, we can draw in our xy plane if we want to, but we could have just whatever kind of graph here, and that's a one-dimensional object or thing. Okay, one nice way to think about what a graph is what you're really doing is just taking this line segment right here that's part of the x-axis, and then you're just going and you're bending that part into this shape right here. Okay, so now that's going to lead into another vocabulary term that we'll use a lot. So what we've done is taken a straight line and curved it. Okay, and so what I'm really trying to get at here is the idea that the word curve, these are one-dimensional objects. Okay, and so that's the thing. All right, now where does this all tie into calculus? If you remember doing things in your calculus class, we can do calculus on curves. We can find tangent lines and so on. We can find, sometimes use integrals to find areas underneath graphs and so on like that. Okay, but we'll worry about that later. But for now, the key thing is that curves are just one-dimensional objects. Okay, and so, sorry, I erased too much. All right, and so that's the idea that I'm trying to get at here. And now, even if you think about it now, it's something like a triangle. Again, if we're just talking about that boundary, we're not talking about its inside, then that's actually composed of three curves. You remember, a line is a curve. So I have these three curves right here. And so as long as you're composed of a finite number of one-dimensional objects, then that object will be one-dimensional as well. And so the dimension of a triangle is also one-dimensional. Okay, now again, you got to remember, if we talk about the inside, though, then that object becomes two-dimensional. All right, and even some strange objects here, I could have something that, looks like this. And notice the way I drew that. I drew two curves and connected them. Okay, and so this object too, right here, that would be one-dimensional. Why is that? Because I can think about it as being composed of a finite number of curves. There's this curve right here, and then there's this curve right here. Okay, so curves are one-dimensional objects, and then again, it would be hard to get the equation of this kind of object, but there's points, many points on this graph that do have a tangent line, and so we can do calculus on that, at least in a theoretical sense, and we could do also integral calculus on it. Since it's a closed object, in some sense, we should be able to find the area inside of there. Now, it would require a lot of extra information to do that, but at least in general, we should be able to. So now, let's talk about some two-dimensional things. Okay, and just remember we said that a plane is two-dimensional. Now, to understand how we can do this, let's go back to that line and make sure you understand the idea about what just went on there. And so remember that we said that a line is one-dimensional, and so is a curve. But one way to think about how we get a curve is that we start with a line, like here, or a line segment, and then we curve it somehow. So we start here, and then we just bend it somehow. All right, and then remember also the equation of that thing would have one independent variable. So one way we can think about things that are two-dimensional is we could mimic the idea. The basic two-dimensional object is a plane, which I'll just draw a piece of a plane. So you can think about having some piece of paper like that. And just as we formed one-dimensional objects by curving a line, we could do the same thing here with this plane, and we could curve parts of it like this, okay? And but we would need to curve every point of that piece of paper or whatever, and what we end up with is an object here that looks like a bent piece of paper, right? Like that. And so we end up with something that basically looks like this. It's very interesting too. Notice that that's actually composed of an infinite number of curves. So if you have a finite number of curves, it stays one dimensional, but if we have an infinite number of curves, we get this kind of object. And this kind of object right here is called a surface. Okay, like that. And so surfaces are two-dimensional objects. All right, like that. And so it's a pretty neat thing if you think about it. All right, so the way to think about a curve is taking a line segment and contorting it in some way or curving it in some way. The way to think about a surface is taking a piece of paper and contorting it or curving it in some way. All right, like that. And so these are our basic two-dimensional objects. Now, doing calculus on these are a little bit different because is there an idea of the derivative? Well, since this thing is composed of infinitely many curves here, okay, like that, on each one of those curves, let's just think about being at some point on that surface. Okay, there's actually two tangent lines right there that I've drawn. Okay, and so since there's two tangent lines, there would be a tangent line going this way and a tangent line going this way. And so what that's telling us is that there's not an actual single derivative at this point. And also, I drew my curves going that direction, but I could have drawn my curves going in this direction as well. Just trying to find a good color. I could have drawn my curves going in this direction as well. So there's also a derivative going in that direction right there. What we'll see later, again, this is just an overview. Don't don't overthink this. But what we'll see is that there's actually a little tangent plane right there. Okay, and in deeper treatments, people call that the tangent space. All right, and to try to connect all these ideas, people use this idea of a tangent space. And for one dimensions, the tangent space is the tangent line. For two-dimensional objects, the tangent space is a tangent plane. Okay, but notice that tangent plane is composed of an infinite number of tangent lines. I know it starts sounding strange after a while. Okay, but that's the idea. So mostly what we're going to do in here in this class is study from the calculus and algebraic standpoint curves and surfaces. Okay, now again, notice that this is a two-dimensional object, but we drew it in 3 dimensions. And that happens a lot of times. We can also draw a curve in 3 dimensions. Now, again, if you're not worried, used to 3 dimensional coordinates, don't worry about it. But what we actually do is we take our old XY plane and then we add on a depth component right here, another axis, and we'll call that the Z axis. Okay, and so you can see that I could draw that surface in that coordinate system, and so we'll get equations for that. And since a surface is 2 dimensional, there will be 2 independent variables. Okay, like that. And in a previous video, I showed you a 3 dimensional graph. The equation of that was z was equal to x squared minus y squared. So here you have this single dependent variable, and then we have these 2 independent variables. All right, like that. But we can also describe curves in space. And so here I have x, y, and a z, like that. And I could have a curve that kind of just, think about a bug flying around in space, like that. Okay, that's a curve. And that's 1 dimensional, but it's drawn in 3 dimensions. Okay, the key thing about this, and this is what this one part will be important about it, whenever we get the equations of this thing, there will only be one independent variable because it's 1 dimensional. It's a curve. All right, and so keeping up with the idea of dimension is going to be important. Okay, and so just one last thing to point out, some other 2 dimensional surfaces you might not be aware of or might not see immediately from this video. But think about a ball, which we call a sphere, right? All right. In a sense, we could go and cut that thing open and flatten it out. It would look a little bit strange. I'm not going to be very good at drawing it, but we could somehow cut and flatten that out where it might look like 2 pieces of circles or something like that. And so it fits in the plane. And so this is actually 2 dimensional. Okay, like that. All right, and so spheres are 2 dimensional. Again, if we're just talking about the border, okay, if we're talking about all of the sphere, including the inside, that is actually 3 dimensional. But if we're just talking about the surface of a sphere, here we heard that word surface. That's a key. That's a hint right there. All right, if we're just talking about the surface of the sphere, that's 2 dimensional. Okay, and even something like a box, as long as we're not talking about the inside of it, okay, if we just think about a box by itself, okay, that's actually 2 dimensional. Why would we say that this is 2 dimensional? Because here's a piece of a plane, here's a piece of a plane, here's a piece of a plane, and there's 3 more not drawn in the picture. So a box is actually composed of 6 pieces of planes, and that's a finite number of planes. So a box is 2 dimensional as long as we're just talking about that border, and so on. Okay, and there's even stranger surfaces out there, but we'll mostly deal with that. So what I'm trying to get at here, the idea, and that it'll end up being a kind of a break point of the course about how we treat this, is we have these 2 basic terms, curves and surfaces. Okay, and the key thing is curves are 1 dimensional, all right, and surfaces are 2 dimensional. And whenever we get to equations, curves will have 1 independent variable, okay, and surfaces will have 2 independent variables, okay, like that. By the way, too, we'll see later with that sphere, just to show you one other thing here. With that sphere, we'll see that its equation is actually equal if the center's at the origin. Let me just try to make this as basic as I can for us. But if the center's at the origin, then its equation would be x squared plus y squared plus z squared is equal to its radius squared. So this doesn't look like, it looks like you have 3 variables there. But remember, I can solve for one of them. Let's just say I solved for z. I would end up getting, because we're going to have to take a square root, we would have plus or minus the square root of r squared minus x squared minus y squared, like that. And so here you have this one dependent variable. Remember, the radius is a constant. And so here I have these 2 variables that z depends on. And so that's another way to see that the sphere is 2 dimensional. Okay, so in terms of the breakdown of the course, we got some basic stuff to deal with that is called vectors. Vectors are important tools to help us analyze things in space. And then we have to talk about doing things in 3 dimensions and higher dimensions. But then once we get through that, we'll do a section on curves and all the algebra and calculus associated with curves, namely curves in space. Okay, and then after that, we'll do a section on surfaces and talk about how to do calculus on surfaces. And so we'll talk about all kinds of derivative things and integral things. So that's kind of the breakdown. And then always keep in mind we can extend to higher dimensions. Okay, there's no problem extending to higher dimensions. And the key thing is the dimension is the number of independent variables. Okay, so think about a meteorologist trying to predict the weather the next day. The meteorologist has to factor in all kinds of variables: the relative humidity, the past conditions, and so on like that. There's all kinds of variables to try to model the weather, and so they could be looking like they could be working in something like a 10-dimensional space. Same thing in finance to make predictions about some kind of financial model. There's all kinds of variables that affect that, and so the number of independent variables in a model is the dimension of the space. So although we can't perceive higher dimensions, there's a lot of practical situations where we're actually working in higher dimensions, maybe without realizing it. All right, so that's about it for now. I hope that at least gives you an idea about what we're going to be talking about, and let me know if you have any questions. All the best.